Dan and Diane get us to the hype of keeping secrets in a type, disallowing creation of some optimization that just might tell the feds what you type.
Hello, everybody. I'm Dan Sprenkels, and I'm here with Diane Hosfelt, and we will be talking about secret types in Rust. So, the main gist of this talk will be that like some of you may know that cryptographic engineers tend to write a lot of their code in assembly, and there's a good reason for that, and I will explain why that is. But as a cryptographic engineer, or an aspiring cryptographic engineer, I'd like to write my code in Rust instead. However, because of some of the compilation quirks in Rust, that's not really a good idea, and I will explain why that is the case, and what needs to be done to make Rust a programming language that we could actually use for cryptographic code. While this talk is pre-recorded, both Diane and me are here in the at the conference and in the chat, so feel free to ask any questions either at the end of the talk or just put them in the chat during the talk, and we will take care of them.
Hi, I'm Diane Hosfelt, and this is Batman. And before we get started, I have a short disclaimer. All of this work was done while I was a Mozilla employee and in no way reflects Apple's views.
Okay, so I will explain a couple of things and then Diane will take over. First, we'll talk about how timing side channels work. What are timing side channels? Why are they dangerous? And then we'll talk about how Rust is not suitable to write code that is actually that actually prevents these timing channels. We'll look at a couple of hacks that we could use to prevent some of these channels in Rust. But then we will go more in depth and look at the RFC on secret types to see how we could actually make Rust more suitable for side channel resistant code. So first,
a side channel is any attack based on information gained from the implementation of a crypto system, not a weakness in the system itself. In this case, we're concerned about timing side channels, which occur when attackers analyze the time taken to execute a cryptographic system algorithm. This can be seen as an implicit output. For example, imagine that it takes less time to execute part of the code when a bit is 0 than it does when a bit is 1. That difference is measurable and can lead to key recovery attacks. These attacks are a particular threat in the post-Spectre world. They're primarily used to attack secrets that are long-lived, that are extremely valuable if compromised, where each bit compromised provides incremental value, and where the confidentiality of compromise is desirable. The fix is constant time code, or to be more precise, data invariant code, where the time it takes to execute the code doesn't depend on the input.
let me explain to you why at this point it's really hard for us to guarantee that the compiler is constant time. So this story will be true for basically any programming language that is compiled. There are some exceptions, but we're at the Rust conference, so let's focus on Rust. So the main problem here is that compilers are, in some sense, problematic. So compilers are allowed to optimize anything that they feel does not change the program, and the behavior, like, or the runtime of a program and stuff like that is not considered to change the program in the view of a compiler. So the compiler might actually optimize stuff that we don't think should be possible. And so, for example, there is this thing that LLVM could do, which is eliminating conditional moves that may load. And let me show you an example of this. Okay. So what you see here on the left is I have written this nice little CMOF function. And what this CMOF function is meant to do is it should, so if this conditional value is true, what it should do is it should move the value in B into A. And if this conditional value is false, then A should just remain the same value and B should just be dropped and thrown away. But the important thing here is that that conditional value is secret. We don't want to leak any information about this secret value. So the runtime of this function should be always the same the same length, the same duration, like depending on the value of this conditional value. So what we do first is we generate a mask from this conditional value, and the value that will come out of this mask will be something like either only once, or if the conditional value is true, if the conditional value was false, it will be a mask of only zeros. And then we will use this mask. So the first line here, what this does is, if this mask is only once, so if the conditional value was true, then it will XOR the value in A with itself. So this will set the value in A to 0. And then only if this conditional value is true, it will XOR A again with B. And A was 0 here, so A will become A will get the value of B. And then if this conditional value was false, and then this mask would be all zeros, then both of these AND operations will make sure that this value is 0 and this value is 0. And both of these operations would be a no-op. And then A keeps the same value. And now what we see when LLVM compiles this, and Rust compiles this, is that the compiler is smart. So the compiler sees, hey, this behavior of this function completely depends on this conditional value. So first what it does is it checks, is this conditional value, is it actually 0? So is it false? And if it sees that this conditional value is true, it jumps to this instruction. So it skips this complete instruction. And if this conditional value was false, then it just does this instruction, then moves the other instruction, and that's it. So basically in one of the two cases, it skipped this instruction. And the important thing to see here is that depending on this value, depending on the value of the conditional, the runtime of the algorithm changes. And so here we have a case where the compiler introduced a side channel, which could be a side channel vulnerability. And the interesting thing is that if we only look at the source code in Rust, it looks like something it looks like code that feels completely like this should be implemented in constant time. Like we have this bitwise AND operation, this bitwise AND operation, and then these XOR operations, and you don't even see them in the compiled code, because LLVM is smart enough to see that they are not needed. And this is actually a pretty big danger for us. So that's what we mean when we say that compilers are a bit problematic.
Obviously, we're at RustFest, so we've all bought into Rust. But the question remains, if we can do secret invariant programming with assembly, why do we need to do it in Rust at all? Writing cryptographic and other security critical code in high-level languages like Rust is attractive for numerous reasons. First, they're generally more readable and accessible to developers and reviewers, leading to higher quality, more secure code. Second, it allows the integration of cryptographic code with the rest of an application without the use of FFI. And finally, we're motivated to have a reference implementation for algorithms that is portable to architectures that might not be supported by highly optimized assembly implementations.
So then why do we focus on Rust? Why don't we just, if we cannot write secure code, why do we want to use Rust in the first place? And that's well, obviously everybody here has their idea of why they use Rust. And in our case, it's kind of the same. So we want to use Rust. The reason that we want to use Rust is because we have all these types and all these nice checks in the compiler that allow us to make our code that's easier to write secure code. And we want to utilize these checks and these tools as much as possible, because writing just plain assembly is really hard and super error prone. And then there's the other thing, that if we only write assembly, well, then you have written an assembly for an Intel processor. When you want to run the same code on an ARM processor, you have to rewrite the whole code, and we don't want to do that, because it also allows you to make more mistakes. And we want our crypto code to be really secure. So we would like to use a high-level language if that is at all possible. So it's not at all bad. So there is some way how Rust can be, in a way, side channel resistant. And this like a couple of these so in Rust we can like make these new type style wrappers around integers. So a struct that only has some integer type, and implement some operations on that are presumably in constant time. And there's two main examples in the wild. The first one that I'd like to mention is the subtle crate from the Dialect Crypto team, which, if you ever need to do some kind of stuff in constant time, use this crate. This is the current state of the art that we have. This is probably what you should use, and we don't have anything better at the moment. And the other example that I'd like to mention is the secret integers crate. The secret integers crate is a bit more academic of nature. What it does, it looks at like, what if we would replace all of the integer types with some kind of constant time integer type? Would that work? And what the secret integers crate does, it provides side channel resistance on the language level. So on the language level, you're sure that your code looks like something that should be side channel resistant, but the secret integers crate does not actually prevent these compiler optimizations that might introduce vulnerabilities. The subtle crate does that, and that is why I recommend that crate. But both of those crates, they are only a best effort. They're only best effort, and they don't guarantee all of the they don't fix all of the compiler optimization issues. Okay, so that is the language level. We can also look at like more at the compiler level. What do we need to do in the compiler to actually do it right? And it turns out we need to add some kind of optimization barrier for the secret data. So let me go back to the example real quick. So it turns out that the problem here is that LLVM seems to be able to completely eliminate this mask variable. So this mask variable is secret because it directly depends on this conditional value which we said was secret. And then because LLVM can just analyze through this mask variable, it can do this really nice optimization of adding a branch and then just eliminating all these bitwise operations. So what we need to do here is we need to add an optimization barrier to this mask variable. And there is a couple of ways that we can add optimization barriers, and the first example is that we can add an optimization barrier by adding an empty assembly directive. So what we do here is we construct an assembly directive which takes this mask value as an input and also takes this mask value as an output. And then LLVM is not able to reason about what happens inside of that assembly directive. Like, we know that nothing happens inside that assembly directive, but LLVM cannot reason about that. And because it can't, it will actually keep this mask value completely intact, and it will not be able to optimize through that variable. And then the other trick, so the assembly directive doesn't work on stable Rust because for the assembly directive you need to have a nightly Rust version to compile, so that's not really optimal. And And so the other trick that we can use is to do a volatile read of secret data. And what this does is it guarantees that at some point this mask value would have existed on the stack. And because of that, LLVM is also not able to optimize through this this volatile read. Both tricks kind of work in 90% of the cases. They do not have like 100% success rate for all cases. I won't go into why that is at this moment, but it's important to know that they don't always work. They are best effort tricks, and the most important part is that although these tricks might work at the moment, they are not guarantees, and the compiler might change in the future. So perhaps in 5 years, the compiler is actually able to look into this assembly directive and see that nothing happens, and it might eliminate that assembly directive completely. And we don't know. We don't have any guarantee that this kind of stuff won't happen in the future. So it might be that in a couple of years, a completely secure version of some software now might actually be insecure with a new compiler version, which I find very scary. So yeah, we'd like to have guarantees, and we don't want to have just hacks. So for the next part, I'll give the floor to Diane, and she will be talking about how we can use secret types in Rust to actually make our lives a little bit better.
So why aren't these language level protections good enough? The compiler and instructions. It turns out that the general purpose instructions on various platforms take a variable number of cycles. So for us to truly have secret independent runtimes, we need to completely eliminate the problematic instructions. This can't be done at a language level, only at a compiler level. Enter RFC number 2859. This RFC defines various secret primitive types and the instructions that should be defined for each type. For all of the extra types, we implement all of the normal acceptable operations. When we know that a value is safe, we can use the declassify function to convert it back to a public value. Using these integer types, we can build more complex types. For example, a secret key may be an array of secret U8 bytes. These types keep us secure by disallowing any Rust code that would result in insecure binary code. So for example, we don't allow indexing based on secrets. We don't allow using secret bool in an if statement. We don't allow division, which is a non-constant time algorithm. We don't allow printing of secret values. And we say that every time we combine a public value with a secret value, the result is also a secret. To give you an example of how this would work, here's a mock-up error message of what would happen if we broke one of these rules. Here, the programmer chose to branch on a secret bool. In this case, the compiler should give us an error because that's not allowed. Now, there are two parts to this problem. There's an LLVM part and a Rust part, which I've already described. There's been some work in the LLVM realm to propose a similar RFC to this one, which we've worked together on at Hacks 2020. We're not entirely sure what the status of that work is at the moment, but what LLVM needs to do is make sure that our constant time Rust code is also compiled safely. So LLVM needs to make sure to guarantee that what we wrote down in the code is still safe in the emitted binary. That means no branching on secret, no indexing with secret indices, and no variable time instructions. At the moment, zeroing memory is out of scope. But when we have this information about public and secret values, then we've laid the groundwork to support that as well. Thank you so much for your attention. If you have any questions, feel free to ask us. While this is a recorded talk, we're currently present and ready to answer questions.
All right. Thank you so much, Dan and Diane. We're lucky enough to have you both here for a Q&A. All right, so you've been joined by your friend too. Mine's
Yeah,
been
Batman came back.
entirely too ignored during the day, right? People looking
Yeah.
at their screens all day. How dare they? So we do have a couple of questions from the audience, which is great. The first one we've got is that this is all very complex. And how do you discover these kind of problems, and how do you even begin to think of a solution? Very broad, but I think it would be great to hear your insight on this.
So there are tools that you can use, formal verification tools that can determine if on different inputs there are different runtimes. So that's one of the ways that you can determine if a program has non-secret independent runtimes for part of it. Dan?
So the way we discover these kinds of issues is like at some point, sometimes I write a piece of assembly, and the first thing I do before I write some piece of assembly is actually just program it in C or Rust and then see what the compiler tells me to do. And then these are the moments that I stumble on these. Hey, wait! But if I would do this, this would not be secure. And that's when I first discovered this for myself. So yeah.
Cool. I mean, it's really cool that you like you said that you gave us kind of an insight on you try and see what the compiler tells you first, and that's how you can discover it. Yeah, I guess just be curious about what the compiler actually tells you, not just like, all right. Someone has asked if there's a working group working on it, on a solution, I suppose.
There isn't a working group. There's just the RFC, which has been a little bit stale because, life gets busy. So if anyone's interested in commenting on the RFC and trying to, help me bring it back to life, that's definitely welcome.
Really cool. I mean, if there's interest for a working group, then yeah, maybe someone will hop on from the audience.
Yeah, that would be great because one of the things that needs to happen is on the Rust side and on the LLVM side, we're going to have to eventually do some implementation work. It's not enough to just define what has to happen. We also have to implement these instructions on the secret types. So that'll actually be a lot of work.
Yeah. So we actually seem to have very little time left, but there was a lot of chatter in the chat room. So I guess people can find you in there, and we can get a few more questions. There were lots of questions, and we just didn't have enough time. But thank you so much for joining us. It was really great to have you here. And oh, Batman! Let me see if I can get. She's asleep. She's melted into a puddle.
Oh, say bye to your new friend. Bye.
Thanks, Fiona. All right, then. See you both. Thank you for joining us.
Thanks so much.